Hello. Here we'll be looking at the practice of fitting randomized block models to data. The data that we'll be looking at come from Sokol and Rolf biometry, and they deal with the weights of tribolium or flower beetles of different genotypes, wild, red and hairy, and the data were collected in 4 separate experiments, 1 to 4. So to begin with, let's read these data in. You'll see that I've got a single vector for the weights. The experiments are coded as factors rather than as numbers per se, and they go from 1 to 4, such that we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. The genotype are wild, red and hairy, and each of those elements in that vector, wild, red and hairy, are repeated 4 times. So we have wild, 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 red, 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 and so on. So there are the data read in. Now we need to simply plot the graphs out, which we'll be doing just now with a strip chart to allow us to have a look at these data. So let's have a look. And here we can see, just by looking at genotype alone, here there does seem to be overall a higher average weight for the red genotype than the hairy. But of course, to be more objective about this, we need to conduct a more formal analysis. Let's begin by doing something that we wouldn't really do normally, but it helps to actually see the power of the randomized block design. So what we're going to do first of all is fit a simple model in which we're examining the relationship between weight and genotype, effectively ignoring the experiment. So this is a one-way analysis of variance because we have a categorical predictor, genotype, and we're interested in its effect on weight. Let's have a look at the breakdown of that one-way analysis of variance. Well, what we see is that in this instance, we can't reject the null hypothesis that the genotype has no effect on the weight of the beetles. Here we have a relatively high probability such that the probability of us obtaining our test statistic or a more extreme if the null hypothesis is true is quite high, and so we do not reject that null hypothesis. Now let's do the more appropriate analysis in which we also investigate the role of the experiment. Why is that helpful? Well, it will primarily account for variability that would otherwise be treated as noise in our experiment. So here is our results 1, which we'll call it. It's the fit of a general linear model of weight related to both genotype and experiment. And you'll note that experiment we've asked to be treated as a factor rather than as a continuous predictor. Here is what we get when we look at the breakdown in terms of the analysis of variance table. We have a highly significant effect of the genotype and of the experiment. So both genotype and the experiment explain variability in the weight of our beetles. Now you remember that R conducts a type 1 sum of square analysis of variance by default. And you might wonder, well, would we get the same if we change the order of entry of experiment and genotype into our data, rather like here if we fitted a model with experiment first and genotype second? Well, in this case we've got a completely orthogonal design in that we've got the same number of replicates, i.e. 1, of each genotype for each experiment. And so our predictor variables are in no way collinear with one another. You cannot guess the experiment from knowing the genotype or vice versa. Because of the lack of collinearity, what we will find is the experiment and genotype have exactly the same significance values, because really we do not need to control for the effects of the other because they are not in any way collinear with one another. Now let's plot out the residuals here just to evaluate whether our assumptions underlying the fit of our model are appropriate. And to begin with, it sometimes helps to actually put your residual plots on the same single graphing page. And so I'm going to be calling up the graphing routine here with a single row, 2 columns, and our plots are going to each go into the columns. Here's the first plot, and that will be the residual plots to test for homogeneity of variance. And here is the second one, which will be used for evaluating the assumption of normality. And we can see from these graphs that broadly speaking, we don't have anything to worry about with regard to homogeneity, and the normal QQ plot appears relatively linear. So we've established that our fit of our randomized block model suggests that genotype has a very strong influence on the weight of our beetles. But also we've learned something extra in that the experiment also influences those weights that have been measured. And of course that might be something that could be followed up. Now, having found a significant effect in our analysis of variance, and because we fitted a relatively simple model, i.e. model without any interactive terms or anything extra, we can actually conduct an honestly significant different two-key test in order to evaluate what individual levels are contributing most to those differences. Now, because we're primarily interested in genotype, this is what we're going to be asking for here. So we'll call up 2-key HSD. We have to fit an analysis of variance model back to our results, and we're noting that we want to compare amongst genotypes. Now you'll see here the difference between red and hairy is the one which shows up in terms of the lowest value of the adjusted significance. It's adjusted because effectively we're controlling for the experiment. So here, the primary source of the variability between genotypes derives from the differences between the red and the hairy genotypes, which is what we saw originally from that strip plot. Thank you for listening to this R-Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.